In this chapter, we'll discuss the chemistry of amines and heterocycles. Many amines exist in nature naturally as alkaloids. Alkaloids are naturally basic compounds that are typically used for self-defense by plants. Typically, alkaloids will have a cyclic amine. They're usually addictive and toxic, and their names typically end with INE to indicate the fact that they are amines. An example of an alkaloid is atropine, which is an alkaloid isolated from nightshade, and is used to dilate pupils, among other things, in medicine. Many alkaloids have useful properties, but unfortunately many of them are also addictive. For example, caffeine, nicotine, and morphine are all examples of alkaloids. Simple primary amines can be named as alkylamines. More complicated amines are typically named by using the suffix amine in the place of the letter E at the end of the alkane or cycloalkane. We typically use diamine and trimine for compounds that have either 2 or 3 amino groups in the molecule. There are also derivatives of amines called anilines, which typically contain an amino group attached to a benzene compound. Here's a few examples of primary amines and how they're named. The first one is terbutylamine, since it contains a terbutyl group attached to an amino group. The next one is another simple amine, which is a cyclohexyl group attached to an amine, so its name is cyclohexylamine. A slightly more complicated example has 2 methyl groups at the 4 position of the cyclohexane. So this is named as 4,4-dimethyl cyclohexaneamine. Now note that you can use either naming system, either an alkylamine naming system or replacing the letter E of the alkane with the amino or amine suffix. Either system is acceptable by IUPAC rules. Aniline, of course, is a compound we previously discussed, which has an amino group attached to benzene. And if we add other substituents, we want to follow the typical naming rules for aromatic compounds. And down here we have an example of a diamine. It has 4 carbons. So this is named as 1,4-butane diamine, since it contains an amino group at the 1 position and at the 4 position. For secondary and tertiary amines, we typically will name them based on whether they're symmetrical or unsymmetrical. If they're symmetrical, we will give the prefix di, tri in front of the alkyl group, followed by the suffix amine. As an example, we have 2 phenyl groups attached to a nitrogen. This is a secondary amine, so we name it as diphenyl to indicate the 2 phenyl groups, and then amine. The next example has 3 ethyl groups on an amine, so we name it as triethylamine. For unsymmetrical secondary and tertiary amines, we typically give the prefix N to indicate that there is a substitution on the nitrogen, followed by the smaller of the alkyl groups. If there are 3 alkyl groups, then the 2 smaller alkyl groups will both have the prefix N. And at the end of the name, we want to have the parent name, which will have the suffix amine. Here's a couple examples. We have a compound, a tertiary amine, that is unsymmetrical. It has a propyl group and 2 methyl groups. So the 2 methyl groups are smaller. And so we give those 2 groups in front of the name. NN dimethyl tells us that we have 2 methyl groups on the nitrogen rather than anywhere else on the parent chain, followed by the parent name, which is propylamine. The next example has a methyl, an ethyl, and a cyclohexyl group. So the methyl and the ethyl will go in front in alphabetical order, starting with ethyl. So N-ethyl, N-methyl, followed by cyclohexylamine. Occasionally, we might need to give the amino group as a substituent when there are other functional groups with higher priority. Here's a few examples to illustrate this. We have a compound that has a carboxylic acid and an amino group. The carboxylic acid is a higher priority group, so we name it as a butanoic acid molecule, which has an amino group on the second carbon, so 2-amino butanoic acid. The next example has 2 amino groups on benzoic acid, and they are on carbon 2 and 4 relative to the carboxylic acid, so 2,4-diamino benzoic acid. Lastly, we have an amino group on the fourth carbon of this ketone, so we name this as 4-amino 2-butanone. In this question, we're going to try to name the following 2 amines based on the IUPAC rules. So in the first example, we have a secondary amine, an unsymmetrical secondary amine. And in the second example, we have an unsymmetrical tertiary amine. The first example in this question has a unsymmetrical secondary amine with a methyl group and an ethyl group. For these compounds, we typically will give the smaller of the 2 alkyl groups first as a substituent on the nitrogen. So we write that as N-methyl, and then the larger alkyl group will be part of the parent name, and so the name or the parent name would be ethylamine. In the second example, we have an unsymmetrical tertiary amine. We look for the largest alkyl group, which in this case is the cyclopentyl group. That's going to be part of the parent name. The smaller groups will be substituents on the nitrogen. We put them in alphabetical order, and we have now for the name N-methyl and propyl cyclopentyl amine. Although we won't spend too much time on naming heterocyclic amines, it's important to know the basics of naming these compounds. Heterocyclic amines, as you might recall, are cyclic amines. We saw a few examples in the aromatic chapters. These compounds typically will have their own parent name depending on which heterocycle it is, and usually the nitrogen will be position 1 in naming these compounds. As an example, we have pyridine, which is essentially a benzene ring where a carbon has been replaced by a nitrogen. Pyrrole is this 5-member ring, which we previously talked about. Notice the nitrogen in each case is position 1. Quinoline, another aromatic heterocycle, has a pyridine attached to a benzene ring. Imidazole, similar to pyrrole, is a 5-member ring, but this time it has 2 nitrogens. One of them will be position 1, the other one will be position 3. Indole is another aromatic compound, which has a pyrrole attached to a benzene. Pyrimidine is similar to pyridine in that it has a 6-member aromatic ring, but it has 2 nitrogens instead of 1. Pyrrolidine is a 5-member ring with no aromaticity, and piperidine is a 6-member ring that is also not aromatic. The nitrogen of a typical amine is sp3 hybridized, which means the bond angles between a nitrogen and the adjacent carbon atoms would be very close to 109 degrees, which is what you expect for a tetrahedral atom. Here's a simple example with trimethylamine. It has 3 methyl groups on a nitrogen. The bond angles between these methyl groups would be roughly 109 degrees, perhaps slightly smaller because of the lone pair needing more space. The lone pair would be in an sp3 hybridized orbital. An amine that has three different substituents on the nitrogen, for example, a methyl, a hydrogen, and an ethyl group, should theoretically be a chiral molecule. However, the two enantiomeric forms of that chiral molecule will rapidly interconvert through a process called lone pair inversion or pyramidal inversion. Here's an example of a theoretical molecule with a nitrogen that has three different groups. It also has a lone pair. The lone pair can be treated as a fourth group, and since all four groups around the nitrogen are different, the nitrogen is considered a chiral center. That means there's two possible enantiomers for this molecule. They're shown on the left and on the right. These two enantiomers will rapidly interconvert through a lone pair inversion that goes through this intermediate that is sp2 hybridized and is planar. Amines with fewer than 5 carbons are generally water soluble, and this is also true for most polar functional groups. If the carbon to heteroatom ratio goes beyond 4 or 5 carbon atoms per heteroatom, then generally the molecule starts to become more organic soluble rather than water soluble. Primary amines and secondary amines contain a hydrogen attached to a nitrogen, and therefore they're capable of hydrogen bonding. As a result, they generally have higher boiling points and water solubility than other functional groups that are not capable of hydrogen bonding. For example, tertiary amines, because they do not have a hydrogen directly on the nitrogen, they are not capable of hydrogen bonding. Primary and secondary amines are considered weak acids. If we use a strong enough base, we can remove the nitrogen to hydrogen proton. For example, an alkyl lithium like butyl lithium can remove the hydrogen on diisopropylamine to form a base that is very useful in organic chemistry called LDA. LDA is short for lithium diisopropylamide. This is a base that we talked previously. We typically use them to make enolates out of ketones, aldehydes, and other carbonyl compounds. Amines are better known as a basic functional group, and so they react with several acids. Their basicity is typically measured by the pKa of the conjugate acid that forms from a reaction with an acid. The larger the pKa of the conjugate acid, that means the weaker the conjugate acid is, and the stronger the amine base will be. Here's a general example of an amine reacting with an acid, forming an ammonium salt, which would be the conjugate acid. Measuring the pKa of this conjugate acid will indirectly give us a sense of how strong of a base we have with the amine. On this slide, we have a list of several amines and a list of the pKa values of their conjugate acids to measure indirectly how acidic these compounds are. Ammonia, when it reacts with an acid, becomes an ammonium salt. In other words, it will have 4 hydrogens and a positive charge on the nitrogen. This is the conjugate acid that forms when it reacts with a Bronsted acid. The pKa of that conjugate acid is 9.26. You might recall that we mentioned that the higher the value, the stronger the base is. So the pK value really refers to how acidic the conjugate acid is, and the higher it is, the less acidic the conjugate acid is, which means the stronger the base. Comparing ammonia to the next example, which is ethylamine, notice the pK value goes up for the conjugate acid, which means this is a stronger base than ammonia. One way we could rationalize this is that the ethyl group is an electron donating group, and so we can think of that nitrogen as being more electron rich, and it can react with an acid easier. Another way to think about it is the stability of the conjugate acid. So when ethylamine reacts with an acid, it will form the following conjugate acid. So NH3 plus an ethyl group will also have a positive charge on the nitrogen. This ethyl group is an electron donating group, so it helps to stabilize the positive charge on the nitrogen. It makes this reaction more likely compared to the reaction with ammonia. The next example follows the same trend. So we have diethylamine, two ethyl groups, which are both electron donating. So the pK value of the conjugate acid is slightly higher, which means the base is slightly stronger than ethylamine and also ammonia. The next example is a typical amide. This nitrogen on the amide is tied up in resonance with the carbonyl. So the lone pair on the nitrogen moves or can be used to move electron density into the oxygen, creating this other resonance structure. As a result, that nitrogen, although at least the lone pair on it, is not readily available to react with an acid or even electrophiles. So for that reason, it's a relatively poor base, as shown by the pK value of the conjugate acid. The next two examples show pyridine and pyrrole, which we talked about previously. Note that the lone pair on pyrrole, this compound here, is required for the aromaticity of pyrrole, and so it's not as readily available as the lone pair on pyridine, which is not necessary for aromaticity of pyridine. And so that's illustrated by the pK values of their conjugate acids. So pyridine is a stronger base since the lone pair on the nitrogen is not required for aromaticity. Aniline, compared to other alkyl amines at the beginning of this table, is a fairly weak acid. The reason is the lone pair on the nitrogen is tied up in resonance with the aromatic ring, as shown by this resonance structure. As with many acidic and basic functional groups, substituents on a compound will affect the acidity or basicity of that functional group. Anilines, like many amines, are basic, and substituted anilines will be affected by any substituent that is placed around the aromatic ring. For example, if we add an amino group, the pKa will go up slightly for the conjugate acid compared to not having that substituent. The same thing occurs with a methoxy group or a methyl group. These are groups that are considered electron donating. And so if you imagine having one of those groups here, we can push electron density into the ring, which means also that this nitrogen is more electron rich. It is going to be a better base compared to not having those substituents on the ring. The halogens, a nitrile and a nitro group, are all groups that are electron withdrawing, and so they will make the nitrogen less electron rich, and so it will be less of a base compared to not when those substituents are not in the ring. In this question, we're going to do a comparison between the basicity of dimethylamine and pyridine. The pKa values of their conjugate acids are given in the question. For dimethylamine is 10.73 and for pyridine is 5.25. Pyridine, you might recall, is an aromatic compound that is a 6-member ring involving 3 double bonds, 1 nitrogen atom, and 5 carbons. In this question, the pKa values of the conjugate acids of the two amines we're comparing are given. For dimethylamine, the pKa of the conjugate acid is 10.73, while the pKa value of the conjugate acid of pyridine is 5.25. Based on these values, we can determine that the conjugate acid of dimethylamine is a weaker acid, which means the base, dimethylamine, is a stronger base than pyridine. In this question, we want to rank the following compounds in ascending basicity. We have 3 molecules: para-nitroaniline, para-aminobenzaldehyde, and para-bromoaniline. In this question, we want to rank 3 different substituted aniline compounds in terms of their basicity. In questions like these, we often get a mix of electron donating groups and electron withdrawing groups, but in this particular question, all 3 examples involve an electron withdrawing group. In order to figure out this question, we want to think back at electrophilic aromatic substitution, and you might recall that we had halogens rated as a weak deactivating group. In other words, is a electron withdrawing group that is only a weak electron withdrawing group. Aldehydes, like most typical carbonyls, were considered moderate deactivating groups. In other words, they're stronger electron withdrawing groups than halogens. And we also talked about nitro groups, which are strongly deactivating in terms of the electrophilic aromatic substitution, which means they're very strong electron withdrawing groups. So that sort of gives us a hint in how to answer this question. Generally, electron withdrawing groups will make an amine, including anilines, less basic. So for example, this para-substituted nitro compound will have a very strong electron withdrawing group that makes this nitrogen a very poor base, since it is very electron poor. The next example, with the aldehyde, we have a moderate electron withdrawing group. It makes the nitrogen electron poor, but not as much as the example with the nitro group. And then the bromine, again, is an electron withdrawing group, but it's a weak electron withdrawing group. And so this should be the most basic out of the 3. If we had an example with an electron donating group, that should be a stronger base than any of these 3 molecules. The Henderson-Hasselbalch equation is an equation that we often use to calculate the pH of a buffer solution. A buffer solution consists of a weak acid and its conjugate base, and in some cases it'll consist of a weak base and its conjugate acid. Buffer solutions are typically used to resist drastic changes to pH. The Henderson-Hasselbalch equation is as follows, where pH of the buffer solution is equal to the pKa of the acid in the solution plus the log of the concentration of the base over the concentration of the acid of the buffer solution. If we rearrange this equation, we can also get a ratio between the concentration of the base in the buffer solution over the concentration of the acid in that same buffer solution. since the equation can be rearranged to be log of the concentration of the base over the concentration of the acid is equal to the pH minus the pK of the acid in the buffer solution. Note that the physiological pH is typically around 7.4. So it ranges between 7.35 to 7.45, which is the typical pH of human blood as well as other bodily fluids. At physiological pH, most amines will typically be protonated, and an amino acid will be found in the ammonium carboxylate form. As an example, alanine, which is shown here, the nitrogen or the amino group is protonated and the carboxylate group is deprotonated. So we have a carboxylate and an ammonium form for the amino acid. Although organic chemists don't use the Henderson-Hasselbalch equation too often, I wanted to show you an example of how this equation can be applied to buffers. In general, we use the equation to solve for different terms within the equation. For example, the pH of the buffer, the pKa of the acid in the buffer, the concentration of the base, the concentration of the acid, or the ratio between the base and the acid. In this problem, we're going to calculate the percentages of the neutral and protonated forms of pyrimidine. In other words, the ratio between the base and the acid in this buffer. Pyrimidine is a molecule that we previously discussed, which has 2 nitrogens and 4 carbons. It is an aromatic compound. The conjugate acid of pyrimidine is pyrimidine with a proton on one of the nitrogens and a positive charge on that nitrogen. It actually doesn't matter what the structures of pyrimidine and the pyridinium ion are as far as solving this problem. In this question, we're going to be dealing with a solution of pyrimidine that is 0.001 molar at a pH of 7.3. As you'll see in a moment, the concentration of pyrimidine actually does not matter since we're going to be solving for a ratio. The pKa of the acid in this buffer, in other words, of the pyridinium ion, is 1.3. Here is one form of the Henderson-Hasselbalch equation. If we plug in the pH, which is given in the question, is 7.3, and we subtract the pK of the acid, which is 1.3, we'll solve for 6. Next, we're going to take the anti-log of both sides of the equation to get rid of the log on the left side. That means we're now going to have the anti-log, or take the anti-log of 6, which is 10 raised to the 6. What this is telling us is that the ratio between the base, in other words, pyrimidine, and the acid, in other words, the pyridinium ion, is 10 raised to the 6 over 1. In other words, there are 1 molecule of the pyridinium ion for every million pyrimidine molecules. So virtually at this pH, 7.3, all of the pyridine molecules will be in the neutral form rather than in the acidic form. Let's now discuss ways we can make amines, and we're going to start with reactions that we are familiar with. One of the reactions we previously discussed was conversion of a primary or secondary alkyl halide through an SN2 reaction with sodium cyanide to have access to a nitrile. The thionyl group would attack the carbon with the leaving group to do a substitution reaction. Reduction of the nitrile with lithium aluminum hydride will give us a primary amine. Note that this route will always give us a primary amine. Another way to make amines would be starting with a carboxylic acid, adding thionyl chloride to convert the OH into a chloride. And then if we add ammonia or another amine, we can do a substitution reaction to give us an amide. If we use ammonia, we will get an NH2 group on the amide. If we use a primary or secondary amine, we would have a substituted amide here. Reduction of the carbonyl of the amide with lithium aluminum hydride will give us the amine. If we use ammonia in the beginning to make the amide, we're going to end up with a primary amine. If we use other amines in this acyl substitution reaction instead of ammonia, we're going to get secondary or tertiary amines instead. If we have a nitro group, we can reduce it into an amine. For example, an aryl nitro group can be reduced with hydrogenation. Hydrogen and platinum or other metal catalysts will reduce the nitro group into this aniline. The nitro group can also be reduced under metal reduction. For example, tin dichloride and an acid like HCl will give us an aniline. Other metals will do the same reaction like tin and iron as well. In this question, we want to propose a structure for either a nitrile or an amide that could be used as a reactant in order to make N-ethyl aniline, which is shown here. In this question, we want to make N-ethyl aniline, which is this compound here, from a reduction of either a nitrile or an amide. If we were going to use a amide, we could use this amide. If we add a carbonyl at the carbon next to the nitrogen, and we reduce it with lithium aluminum hydride, we'll have access now to N-ethyl aniline. In this particular example, we cannot use a nitrile, so the nitrile that perhaps we can try to use would be this one, benzonitrile. However, when we reduce this benzonitrile, we would obtain aniline instead of N-ethyl aniline. So at least in this example, from a nitrile, we would not have direct access to N-ethyl aniline. We would have to do another reaction in order to add the ethyl group. Another method to make primary amines is by an azide reduction. Azide is an anion that has 3 nitrogens and is actually a nucleophile. And so we can use it with primary and secondary alkyl halides to do an SN2 reaction, where the azide attacks the carbon with the leaving group to give us an alkyl azide. We can reduce this functional group similar to nitro groups by using lithium aluminum hydride, for example, and that would give us a primary amine plus, although it's not shown here, nitrogen gas, which is N2. Another method to make amines is by something called reductive amination. This is a reaction where we combine 2 reactions in one. We first convert a ketone or an aldehyde into an imine, which we then reduce with a reducing agent to give us an amine. Here is a general example using a ketone. If we add ammonia and sodium borohydride, we can end up with a primary amine. The ammonia would replace the carbonyl, give us an imine, which is then reduced the double bond of the imine is reduced into a single bonded carbon to nitrogen bond. If we use a primary amine instead of ammonia, we end up with a secondary amine. And if we use a secondary amine, we will have now a tertiary amine. Here's another example using a ketone. If we add ammonia and sodium borohydride, or we combine the reaction with another reducing agent, which is hydrogen gas plus a metal catalyst like nickel, we can reduce the imine into an amine, as shown here. Here's the mechanism for a reductive amination. It starts off with ammonia or the amine that we're using, either primary or secondary amine, attacking the carbonyl. The oxygen will be protonated by an acid. That would give us initially a carbonyl amine intermediate. The nitrogen will eventually form a double bond, so the lone pair on the nitrogen will form a double bond between the nitrogen and carbon by eliminating the OH group. That gives us an imine. This is a reaction that we covered in a previous chapter. So any aldehyde or ketone, when you react it with ammonia or a primary amine, you typically will get an imine. If we reduce that imine double bond with sodium borohydride or hydrogen and nickel or some other metal catalyst, we can obtain now a saturated product, which would be an amine. A related reducing agent to sodium borohydride is sodium cyanoborohydride, which has a cyano group. The cyano group essentially reduces the reactivity of this hydride reagent slightly compared to sodium borohydride. And this is an ideal reducing agent for reductive amination. It has been found that the reaction can be done all of one single reaction. Combining ammonia, for example, with an aldehyde will give you an imine initially, which would then be reduced by sodium cyanoborohydride to give us a primary amine. Note that this reaction is typically done at slightly acidic pH, somewhere around 3 to 4. Here's another example with a primary amine reacting with a ketone. Sodium cyanoborohydride at a low pH will lead to a secondary amine. And the last example is a secondary amine with an aldehyde with reducing conditions will give us a tertiary amine. There are many biological examples of reductive amination. Here's an example using the biosynthesis of the amino acid proline. Starting with this compound, which has both an aldehyde and an amino group. The amino group, notice, is protonated, and the carboxylic acid is deprotonated due to physiological pH. The amino group can attack the aldehyde, and after removal of a water molecule, so the carbonyl, what remains from it, which is an OH group, is removed as a water molecule, we end up with an iminium ion, which is related to imines. That iminium ion can be reduced by NADH, which is a reducing agent that is found in biological cells. A hydride is added to this carbon to give us proline. In this question, we want to predict the product of a reductive amination between ammonia, acetaldehyde, and sodium borohydride. In this reaction, ammonia will replace the carbonyl and initially give you an imine that looks like this. That imine will be reduced by sodium borohydride into ethylamine, as shown on the product side. In this question, we want to predict which reactants we would use to make N-ethyl 2-phenylethylamine, which is shown here, through a reductive amination reaction. Reductive amination reactions generally combines an amine or ammonia with either an aldehyde or a ketone. And after reduction, we end up with an amine that has an extra alkyl group compared to the amine that we use to synthesize the product from the reaction. In other words, when we look at the product, we can consider the amine coming from the nitrogen attached to either of the two alkyl groups that are in the product, and we add the other alkyl group from either an aldehyde or a ketone. So in this example, we can add this phenyl ring plus the two carbons that are attached to the nitrogen from an aldehyde if we mix it with methylamine and sodium borohydride, or we can add the methyl group from an aldehyde, so that would be formaldehyde, adding it to this amine, and sodium borohydride would give us the same product. Another reaction that is used to make amines, especially primary amines, is the Hofmann rearrangement. This is a reaction that starts off with an amide, and we lose a carbon in the process, the carbonyl essentially of the amide, by using a halogen like Br2 or Cl2 and a strong base such as sodium hydroxide. Here's an example with a primary amide. If we use sodium hydroxide, bromine, and do the reaction in water, we can convert the amide into a primary amine with the loss of CO2. Note that essentially we have lost the carbonyl and we have joined the nitrogen to the alkyl group. In the second example, we're going to use again a primary amide, add sodium hydroxide, Cl2, and water to lose CO2 from the carbonyl and join the amino group to the carbon that is to the left of the carbonyl initially. As a result, we end up with a primary amine. The mechanism of the Hofmann rearrangement involves adding base to an amide. It removes one of the hydrogens on the nitrogen, giving us a negatively charged nitrogen, which is a great nucleophile, which could attack one of the bromines of bromine, eliminate the other one. This gives us an intermediate called an M-bromoamide. The base will then remove the other proton, giving us again a negatively charged nitrogen, which can now trigger the Hofmann rearrangement. One of the resonance structures of this negatively charged amide is this structure shown here, where the negative charge, instead of being on the nitrogen, is on the oxygen of the carbonyl, and we have a double bond between the carbon and nitrogen. That oxygen can now reform the carbonyl by pushing the alkyl group to the nitrogen and eliminating the leaving group on the nitrogen. As a result, we're basically doing a 1,2 alkyl shift that is being forced by reforming the carbonyl and eliminating the leaving group. In the second part of the mechanism of the Hofmann rearrangement, after the alkyl group migrates from the carbon of the carbonyl to the nitrogen of the amide, we end up with this intermediate called an isocyanate, where we have a carbon that is double bonded to an oxygen on one side and double bonded to a nitrogen on the other side. Isocyanates are really good electrophiles. They will be attacked by the hydroxide ion, so the hydroxide ion will attack the carbon. Then the electrons in this double bond will be used to pick up a proton, which ends up on the nitrogen. That results in a carbamic acid. Carbamic acids is not a functional group we often discuss in an intro organic course, but it's a functional group that has a carbonyl, an OH on one side, and an amino group on the other side. This functional group is related to carbonic acids. Again, another functional group we don't see too often in an intro organic course, but is actually a pretty important biological molecule, especially in terms of the chemistry of blood. This is the structure of carbonic acid. It has two OH groups attached to a carbonyl. Both carbonic acid and carbamic acids are unstable and they like to decompose and form CO2. In the case of carbonic acid, we typically have a water byproduct. In the case of carbamic acid, we form an amine instead, as shown by this example. A base will remove this proton, lead to this bond, forming a double bond here. The single bond between the carbon and nitrogen will be used to pick up a proton and add it to the nitrogen. That gives us the primary amine plus CO2 as a byproduct. As we mentioned previously, in the Hofmann rearrangement, we always lose one carbon due to the loss of CO2. As an example, if we start off with a primary amide with 5 carbons, as you can see here, 1, 2, 3, 4, and 5. If we do the Hofmann rearrangement, which involves Br2 and sodium hydroxide, we'll end up with a primary amine that has only 4 carbons, 1, 2, 3, and 4. In this second example, we have a primary amide. With the Hofmann rearrangement, we end up with an amine that has only 3. We're losing the carbonyl carbon in the process, and the amine will be joined to this carbon here. In the last example, again, we have an amide that will be turned into an amine with the loss of the carbonyl carbon, and the nitrogen will be attached to the cyclohexyl group in the product. A related reaction to the Hofmann rearrangement is the Curtius rearrangement. This is a reaction that is used to make primary amines from the thermal decomposition of azo-azides with water, and it leads to the loss of a CO2 molecule. Here's an example using an azo-azide. If we heat it up, we'll get an isocyanate, which will then react with water to lose CO2 and give us a primary amine. Azo-azides is a functional group we don't see very often, and we certainly haven't seen it this semester. But azo-azides can be accessed from an acid chloride or an acid or a carboxylic acid. For example, carboxylic acid, when reacted with thionyl chloride, will be converted into an acid chloride, which can then react with sodium azide, and the azide ion, which is a good nucleophile, will replace the chlorine to give us an azo-azide. There are a lot of similarities between the mechanism of the Curtius rearrangement and the Hofmann rearrangement. In the Curtius rearrangement, we start off with an acid chloride, which when reacting with sodium azide will be converted to an azo-azide. One of the resonance structures of an azo-azide has a negative charge on this nitrogen, and it has a triple bond between these two nitrogens. In the beginning of the Curtius rearrangement, the negative charge or the lone pair on this nitrogen will be used to form a double bond here, which leads to a 1,2 alkyl shift of this alkyl group to the nitrogen by elimination of an N2 molecule. So N2 or nitrogen gas is nitrogen triple bonded to another nitrogen. The result of this reaction gives us an isocyanate, which you might recall was the key intermediate in the Hofmann rearrangement. The rest of the mechanism is essentially identical to the Hofmann rearrangement, where water or the hydroxide ion will attack the carbonyl, the carbon of this isocyanate. That will lead to the electrons in this double bond moving to the nitrogen. The nitrogen can then pick up a proton to get us to a carbamic acid. Carbamic acids, as we mentioned before, are unstable and they like to decompose into CO2 and amines. So the next set of steps simply lead to the removal of a proton from this oxygen to give us this intermediate, which will then form a double bond here between the oxygen and carbon by eliminating the amine to give us a primary amine and also CO2 as a byproduct. Similarly to the Hofmann rearrangement, the Curtius rearrangement always leads to the loss of one carbon as a CO2 molecule. If we start off with an azo-azide that has 5 carbons and we heat it, we'll get a isocyanate, and then water will react with the isocyanate to lead to the loss of CO2 and an amine that has only 4 carbons, as this example shows, since we lost one carbon as a CO2 molecule. The next example has 4 carbons in the longest chain. If we heat it, we get an isocyanate, which when it reacts with water leads to the loss of CO2, plus an amine that has only 3 carbons in the longest chain. Note that we have essentially transferred a nitrogen from the azo-azide directly to this carbon here with the loss of the CO2 or the carbonyl. Last example, we have a cyclohexyl group. If we heat this azo-azide, we'll get an isocyanate, which when it reacts with water will give us an amine and a CO2 molecule. The Curtius rearrangement is a reaction that has been around for a long time and has been used for the synthesis of several molecules. For example, it has been used to synthesize the antidepressant drug shown here. This synthesis starts off with an acid chloride, which when it reacts with sodium azide will be converted into the azo-azide group, and I'm going to abbreviate the alkyl chain as an R group. This azo-azide will be heated. That will lead to the conversion of this azo-azide into an isocyanate. So there's a carbon here. That's double bonded to the first nitrogen of the azide. And the R group that was originally on the carbonyl on the left side will shift. We'll do a 1,2 shift from this carbon to the first nitrogen of the A side. The two other nitrogens will be lost as CO2, not CO2, nitrogen gas, excuse me. And then lastly, when we add water, we're going to turn this isocyanate into a carbamic acid, which decomposes and loses CO2. As a result, this nitrogen and R group will be found in the product as shown here. How could the following amine be prepared from 4-methylbenzoic acid using the Curtius rearrangement or the Hofmann rearrangement? So the question is asking us to synthesize this aniline, or another way of looking at it, a primary amine, from 4-methylbenzoic acid, which is this compound here. This question is asking us to convert 4-methyl benzoic acid into 4-methylaniline, which is shown here. And we want to use a Curtius or a Hofmann rearrangement to do this reaction. If we start off with a carboxylic acid, we can convert it into an acid chloride, which then, if we react it with ammonia, would give us a primary amide. That allows us to now do the Hofmann rearrangement by adding Br2 or Cl2 plus sodium hydroxide, which would then lead to the Hofmann rearrangement, which always involves the removal of the carbonyl as a Cl2 molecule and joining the amino group of the amide with the alkyl group on the left side of the carbonyl, which in this case is a toluene ring. That provides one way to get to 4-methylaniline. The other way would be to react acid chloride with sodium azide, which will give us an azo-azide. Heating the azo-azide in water will lead to the Curtius rearrangement and conversion into 4-methylaniline. In this question, we want to take orthomethylphenylacetic acid, which is the molecule shown here, and convert it through a Hofmann or Curtius rearrangement into orthomethylbenzylamine, which is the following compound, where we have a benzyl group, which is a benzene plus a CH2, attached to an amino group and an orthomethyl group here as well. In order to do the Hofmann or Curtius rearrangement, we want to take this carboxylic acid and convert it into an acid chloride first, which will allow us to make the precursors of both reactions. Adding ammonia to an acid chloride would give us a primary amide. So in other words, we'll have an NH2 group here instead of the chlorine. Then adding bromine plus base, we can do the Hofmann rearrangement where we lose the carbonyl and the NH2 group will attach directly to this carbon to give us the amine product that we want. In the Curtius rearrangement, we want to convert this acid chloride that we originally have and add sodium azide to give us an azide group instead of this chlorine. Heating the reaction in water will do the Curtius rearrangement, where the alkyl group transfers to the first nitrogen of the azide, eliminates the other two, and after the water adds to the isocyanate, we end up with the Curtius product, which is this amine group here. We'll now discuss the reactions of amines, and we're going to start off with a review of nucleophilic azo substitution that involves ammonia, primary amines, and secondary amines. An acid chloride, for example, can react with ammonia to produce a primary amide. The ammonia attacks the carbonyl carbon and eliminates the chlorine to give you this amide plus ACl as a byproduct. A primary amine can do the same reaction to give you a secondary amide, and a secondary amine can react with an acid chloride to give you a tertiary amide. Note that tertiary amines are not able to do this reaction since they're not really nucleophilic. Addition of a tertiary amine to an acid chloride would lead to a nitrogen that has 4 bonds on it and a positive charge, which is not a stable intermediate. Ammonia, primary amines, and secondary amines can react with alkyl halides to undergo alkylation reactions. For example, ammonia will react with an alkyl halide in the presence of base to produce a primary amine, at least initially. Primary amines will react with an alkyl halide, again through an SN2 reaction to produce a secondary amine. A secondary amine will react with an alkyl halide to produce a tertiary amine, and finally, a tertiary amine can also react with an alkyl halide to produce a quaternary ammonium salt. It is generally very difficult to control these types of alkylations. For the most part, the products would usually be more reactive than the reactant because of the electron donating alkyl groups. And so this reaction is usually not used to do an alkylation reaction. The Gabriel amine synthesis is a method that is used specifically to prepare primary amines from an alkyl halide. In this synthesis, we start off with phthalimide, which is shown here, and we add base, which will remove the hydrogen on the nitrogen. It's a very acidic hydrogen. Think of this very similar to 1,3-dicarbonyls. You might recall that the carbon in the center was very acidic. For the same reasons, the nitrogen here in the center is also very acidic. Adding an alkyl halide to the conjugate base of phthalimide will lead to an SN2 reaction, adding an alkyl group now onto the nitrogen. Hydrolysis of the product that is shown here with base and water, or even acid and water, will hydrolyze the 2 amide bonds that are found around the nitrogen and release the amine as a primary amine. The 2 carbonyls will become carboxylic acids as the hydroxyl or the hydroxide ion attacks one of the carbonyls at a time and eliminates the nitrogen. Another equivalent of the hydroxide ion will do the same with this carbonyl. In this question, we want to use an alkyl halide to prepare the following neurotransmitter, dopamine. Notice dopamine has a nitrogen here that is primary since we have 2 hydrogens attached to it. It's also attached to this carbon, which is attached to another carbon, and then that is attached to a benzene ring with a couple of hydroxyl groups. There's a few reactions we can use in order to make dopamine, specifically the amino group. on dopamine, we can, for example, use an alkyl halide and add sodium azide, which will do an SN2 reaction on this carbon by replacing the bromine. That would give us an alkyl azide, which we can reduce with lithium aluminum hydride to produce a primary amine. Another route to dopamine involving an alkyl halide would be to react this alkyl halide with phthalimide after we have added base to it, which would lead to the nitrogen attacking the carbon, eliminating the bromine, and now that alkyl group will be attached to the nitrogen. Hydrolysis of these amide bonds with hydroxide and water would lead to release of the amino group and give us a primary amine as shown here. Another reaction involving amines is called the Hofmann elimination. This is a reaction that converts amines into alkenes. Amines in general are very poor leaving group, very similar to alcohols. And so if we want to eliminate an amino group, we have to essentially activate the amino group. One of the ways we can do this is by adding an excess of methyl iodide, which will turn the nitrogen into a quaternary salt. Following this up with a base and a mixture of silver oxide and water will make hydroxide ions, which will help eliminate the quaternary salt, which is a much better leaving group than the amino group is. This reaction typically gives you the anti-decisive product. As you can see by this example, the base could remove two hydrogens, either the hydrogens on this CH2, that will lead to the decisive product or forming a double bond this way. Instead, one of the hydrogens on the methyl group is removed, and we end up with a double bond on the least substituted carbon, and giving us, in this example, one hexene. Once the hydrogen is removed, the nitrogen will be eliminated this way to give us trimethylamine. The product from this reaction is sometimes referred to as the anti-decisive or the Hofmann product, and is always the least substituted alkene that is possible from an elimination reaction. Here's another example of the Hofmann elimination, starting with this primary amine. If we add an excess of methyl iodide, we'll have now this quaternary ammonium salt, which when we add silver oxide and water and heat it, we'll get two potential products, either the decisive or the Hofmann alkene. The decisive product will result from the hydroxide ion removing a hydrogen from this carbon and giving us a double bond this way once we eliminate the nitrogen. The Hofmann product, which is the major product from the Hofmann elimination, results from removing a hydrogen from this methyl group, which is more accessible, creating a double bond here after elimination of the nitrogen. Here's a look at the mechanism for this reaction, which is essentially an E2 reaction. The hydroxide ion will remove a hydrogen from a carbon that is adjacent to the carbon that has the quaternary ammonium salt. Removal of that hydrogen will lead to forming a double bond once we eliminate the nitrogen. The reason why the Hofmann elimination gives you the least substituted alkene is because the base will have a hard time getting to the more hindered internal hydrogens like these here compared to the more accessible CH3 hydrogens, which are at the end of the molecule. This is in part due to the very bulky multi-substituted nitrogen or the ammonium salt that we form first before adding the base. The Hoffman elimination appears in the biosynthesis of nucleic acids, specifically adenosine. Adenosine is made in part by a Hoffman elimination of this compound here, which involves removing a hydrogen with base, leading to a double bond after elimination of this positively charged nitrogen. That produces fumarate, which has a double bond as shown here. It also releases adenosine monophosphate. In this question, we want to figure out the product that you would expect from the Hoffman elimination of the following amine. Notice this nitrogen is attached to an ethyl group and a cyclohexyl group. When trying to do a Hoffman elimination on an unsymmetrical alkene such as this one, there's two possible outcomes that we can get. The reaction starts by adding excess methyl iodide to the amine that we're starting with. That would lead to adding two methyl groups to the nitrogen and giving us the following intermediate. It will have two methyl groups, an ethyl group that was already on there, and a cyclohexyl group which was already on there. We'll also have a positive charge on the nitrogen. We'll have a counter ion and iodide. Then once we add silver oxide and water, we can do the Hoffman elimination portion of the reaction. The hydroxide ion can remove a hydrogen on this carbon. So let's draw that out. If we have a hydrogen here, we can remove that hydrogen. So base, we'll remove that hydrogen. These electrons will lead to a double bond forming there by elimination of the nitrogen, which notice has two methyl groups as well as a cyclohexyl group. So that would lead to the products that you see on the top, ethylene, as well as this dimethyl cyclohexylamine. The other possibility is that we remove instead a hydrogen from the cyclohexyl group, so base. We remove this hydrogen, form a double bond here by eliminating the nitrogen. When we do that, the nitrogen will be eliminated with two methyl groups and an ethyl group. So for that reason, we get the following two compounds: dimethyl ethylamine as the amine product that's eliminated, as well as the following cyclohexene. The cyclohexene results when we remove this hydrogen and form a double bond there. Since the Hoffman elimination typically goes after the least hinder hydrogen, we should expect that it will be this hydrogen rather than this one that is removed the most. So the products on the top most likely would be the major products. In this question, pretty similar to the last one, we have an unsymmetrical amine and we're going to do a Hoffman elimination, and we want to predict the major products from the reaction. Addition of excess methyl iodide to the amine in this question would lead to the following intermediate that has an ethyl group this way, cyclohexyl group to the left. We'll have a nitrogen going up with an ethyl group on it, as well as two methyl groups plus a positive charge on the nitrogen. we'll have an iodide counter ion. And then once we add base, we can do the Hofmann elimination. Now there are three possibilities here. We can remove a hydrogen from, so if we look at the nitrogen and count 2 carbons away, so this is the carbon that the nitrogen is attached from this side. On this carbon, we can potentially remove this hydrogen. If we go towards the cyclohexyl group, if this carbon has the nitrogen, we go to the next carbon, and we can remove a hydrogen from that carbon. Or if we go upward, here's the nitrogen. It's attached to this carbon, so we could potentially remove a hydrogen from the end here. From those three possibilities, the least hindered hydrogen would be the one here on the methyl group at the end. A simpler way to look at it here is a methyl group. Those hydrogens are more accessible than the secondary hydrogens here, and more accessible than the tertiary hydrogen here. As a result, if base removes the most accessible hydrogen, which is this one, and we form a double bond here by eliminating the nitrogen, we end up with ethylene as our alkene, plus the following amine, which has 2 methyl groups, plus a carbon that has an ethyl group to the right and a cyclohexyl group to the left. The Sandmeyer reaction is a very useful reaction that allows us to convert the amino group in an aniline into a number of other substituents around that are attached to a benzene ring. The Sandmeyer reaction involves reacting an aniline or a primary aroamine with nitrous acid, which is HNO2, to form a diazonium salt. This diazonium salt is very reactive. It's an electrophile that can react with a number of nucleophiles that leads to a substitution reaction of the diazonium salt with the nucleophile. As a result of this reaction, the diazonium salt is released as a nitrogen gas molecule. The diazonium salt in the Sandmeyer reaction, again, is formed by reacting nitrous acid, usually in combination with sulfuric acid, to form or convert the amino group in an aniline to a diazonium salt, which can then react with several copper salts, such as copper bromide, to replace the diazonium salt with the bromine. Another example shown here will lead to conversion of this amino group into a diazonium salt, which then reacts with copper cyanide to add a cyano group where the amine used to be. Copper chloride would do a similar reaction as copper bromide, giving you access to aryl chlorides. Without going too much into the details, it is believed that this reaction occurs through a radical mechanism where the copper adds an electron, leading to breaking the carbon to nitrogen bond, giving us this aryl radical, which then reacts with whatever X group is on the copper. It could be a halogen or a cyano group to give us the final product. Another version of the Sandmeyer reaction involves using hypophosphorus acid, which is H3PO2, to replace the diazonium salt with a hydrogen. For example, this substituted aniline, when reacting with nitrous acid as well as sulfuric acid, will convert the aniline into a diazonium salt, which then, when mixed with hypophosphorus acid, will lead to replacement of the diisonium salt with a hydrogen. Overall, we're completely removing the amino group that was in the starting aniline. Here's a second example, a diisonium salt, which would be formed from an aniline. When mixed with hypophosphorus acid, will lead to the reduction of N2 and giving us a benzene molecule in this example. Diisonium salts can be converted into phenols by heating water with the diisonium salt, as shown by this example. Alternatively, if we use copper oxide or cuprous oxide mixed in with copper nitrate, we can do the same reaction at a lower temperature. The example shown below here, using a para-methyl-aniline as an example, when mixed with nitrous acid and sulfuric acid, will give us the diisonium salt, and then mixing the diisonium salt with water and a mixture of cuprous oxide as well as copper nitrate will turn the diisonium salt into a phenol. The Sandmeyer reaction now gives us another method to add substituents onto a benzene ring. So in combination with electrophilic aromatic substitution reactions and nucleophilic aromatic substitution reactions, we can do a number of manipulations around a benzene ring. Here's a question where we want to prepare meta-hydroxyacetophenone. Of course, this would be a difficult molecule to make based on electrophilic aromatic substitution. We want to use the diisonium salt replacement reaction, or aka the Sandmeyer reaction, to add the phenol group onto this molecule. If we start the synthesis from benzene, we could do an Friedel-Crafts acylation reaction to add the acetyl group in acetophenone. And then if we do a nitration, that would lead to adding a nitro group at the meta position, since the ketone is a meta-directing group. Reduction of the nitro group with tin chloride and acid, which again can be done under other methods such as hydrogenation or lithium aluminum hydride. Either way, we're going to reduce the nitro group into an amino group. Adding nitrous acid and sulfuric acid will turn that amino group into a diisonium salt. Heating it with water, or using water and a mixture of cuprous oxide and copper nitrate, will convert that diisonium salt into a phenol. Heterocyclic amines are, as we mentioned previously, compounds that are cyclic with at least one nitrogen involved. Pyrrole is an example of a heterocyclic amine. It has a nitrogen plus 4 carbons. It is an aromatic compound, as we have mentioned before. Each carbon has a p orbital with a single electron, and the nitrogen will have the lone pair in a p orbital that is aligned with the other p orbitals on the carbons, giving us 6 pi electrons, 4 from each, or 4 electrons from the carbons and then 2 from the nitrogen. Because there are 6 pi electrons, this compound is aromatic. Pyrrole reacts with different electrophiles in electrophilic aromatic substitution reactions. For example, if we mix it with Br2, we'll get a bromination at the second carbon of pyrrole. Now, this reaction actually occurs faster than benzene, since pyrrole is considered a more electron-rich aromatic ring, in part due to this nitrogen, which the lone pair can be donated as shown here. So the lone pair will push electron density this way, the double bond will move this way, and that means that these electrons will be able to attack an electrophile and add it to the second position of the ring. Electrophilic aromatic substitution reactions with perols typically occur at the second carbon rather than the third carbon of the perol ring. The perol ring is symmetrical, so this carbon is the same as that one, and this carbon is the same as that one. If we do a nitration, for example, of perol, the nitro group will add to this carbon in part because the lone pair is pushing electron density towards this carbon. So the lone pair, if we move it here, will form a double bond. This double bond will move here to put a double bond here. And then this carbon will be used to attack the electrophile. Another way of viewing this is that if the substitution of whatever electrophile, in this case the nitro group, adds to the second carbon, we're going to have 3 resonance structures compared to only 2 resonance structures if the electrophile adds to the third carbon. For that reason, we're going to get primarily substitution at the second carbon. Many other heterocyclic amines are found in important biological molecules. For example, imidazole is found in the amino acid histidine, while thiazole is found in vitamin B1. Imidazole contains 2 nitrogens. One of those nitrogens is, at least its lone pair, is part of the aromatic ring of this molecule. As a result, the lone pair on this nitrogen is actually basic, while the lone pair on this nitrogen is not. Since if we use the lone pair on the nitrogen in position 1 to react with an acid, we would then break the aromaticity of imidazole. In this question, we want to draw the p orbitals of a molecule we just saw, which is thiazole. It is a 5-member ring with a sulfur, couple of double bonds, and a nitrogen here. Thiazole is a molecule that contains 3 carbons, 1 nitrogen, and 1 sulfur. The sulfur uses one of its lone pairs to complete the aromaticity of this compound. So we're going to put a lone pair on the sulfur in a p orbital. This carbon will have a double bond to this carbon, and so we're going to put a p orbital on each of these carbons with 1 electron in each. The nitrogen will have a p orbital with a single electron, since it's going to make a double bond to this carbon, and the carbon will also have a p orbital with a single electron. So overall, there are 2 electrons from these 2 atoms, 2 more electrons from this double bond here, and 2 more electrons from the lone pair on the sulfur, giving us 6 pi electrons for this compound to make it aromatic. The sulfur also has a p orbital, a lone pair in an sp2 orbital that would not be aligned with the pi cloud around this ring. The nitrogen will also have a lone pair that is also part of an sp2 orbital that will also be perpendicular to the pi cloud of this compound. As we covered in the aromatic chapter, pyridine is an aromatic compound that contains 5 carbons and 1 nitrogen. Each carbon will have a p orbital with a single electron, and the nitrogen will also have a p orbital with a single electron. That gives us 6 pi electrons for the pi cloud, and pyridine as a result is aromatic. The lone pair on pyridine is not necessary for pyridine to be aromatic, So the lone pair will be in an sp2 orbital away from the pi cloud. Note that the nitrogen in pyridine is typically less basic than a amine that is sp3 hybridized, so a typical alkyl amine. One explanation for this is that the nitrogen in pyridine is sp2 hybridized, which generally means that nitrogen is more electronegative. It holds on to the lone pair tighter compared to an sp3 nitrogen. Pyridine, similar to benzene, will undergo electrophilic aromatic substitution reactions. However, the reaction is generally very slow. In fact, in order to do a bromination reaction, we have to heat pyridine and bromine to 300 degrees just to get a 30% yield of 3-bromopyridine. Pyridine is considered an electron-poor aromatic ring compared to benzene, and Perot, as we mentioned before, is actually considered an electron-rich aromatic ring, and it reacts a lot faster than benzene and pyridine in electrophilic aromatic substitution reactions. Pyridine typically undergoes electrophilic aromatic substitution reactions at the third carbon, which is this one here. The reason for this is once the electrophile adds, we get an intermediate that has 3 resonance structures where the positive charge is always on a carbon as seen here and here. If the electrophile adds to the second carbon, which is this one, we'll have 3 resonance structures, 1 or 2 that have a positive charge on a carbon, but one of the resonance structures ends up with a positive charge on the more electronegative nitrogen atom, which makes this route less likely. The same thing occurs when the electrophile adds to the fourth carbon, which is this carbon. We obtain an intermediate with 2 resonance structures that have a positive charge on a carbon, as shown by these two. But one of the resonance structures has a positive charge on the nitrogen, which again is an electronegative atom. We normally don't want to put a positive charge on electronegative atoms. So this route is also unfavorable, which means typically we see electrophiles adding to the third carbon of pyridine. There are many important polycyclic heterocyclic amines, such as quinoline, isoquinoline, indole, and purine, that contain both a heterocyclic amine as well as multiple rings. Both quinoline and isoquinoline can also react in electrophilic aromatic substitution reactions similar to benzene. However, they tend to be less reactive than quinoline and isoquinoline. Similar to pyridine, quinoline and isoquinoline are considered electron-poor rings. As a result, the reaction is generally slow. Here's an example with quinoline and a bromination reaction, which leads to the bromine adding to the 5th carbon or the 8th carbon in roughly a 1-to-1 ratio. Generally, the benzene is slightly more electron-rich than the pyridine of quinoline. For that reason, we get substitution primarily at the benzene carbons, like position 5 and position 8. With isoquinoline, if we try to do a nitration, again, we're going to get primarily substitution on the benzene ring side of the molecule rather than the pyridine ring, which is less electron-rich than benzene. Indole is considered a aromatic ring that is more electron-rich overall than benzene. Specifically, the pyrrole part of the indole ring is more electron-rich. So substitution through electrophilic aromatic substitution usually occurs in that ring, specifically at position 3. The reason for this is the nitrogen will push electron density towards this carbon by forming a double bond here and using this double bond to attack the electrophile. That would lead us to substitution at the third carbon. Purine has three basic pyridine-like nitrogens. Those would be the nitrogen at position 7, 1, and 3. These nitrogens can react with acid pretty freely. However, the nitrogen at position 9 is more like the nitrogen in indole and pyrrole, which are required to complete the aromaticity of the ring, in this case for indole, as well as for purine. And so that nitrogen lone pair is usually not very basic. Electrophilic aromatic substitution reactions with purine typically occurs at carbon 8 here of the ring. Many important biological molecules as well as pharmaceutical drugs contain heterocyclic amines within their structures. For example, quinine, which is an antimalarial drug, contains quinine. Tryptophan contains the tryptophan ring. Adenine, which is a DNA base, contains the purine ring. The same thing occurs in Viagra. We have a pyridine ring in this coenzyme shown here, and there are multiple pyrrole rings in the molecule heme. In this question, we want to figure out which of the two nitrogens in the following compound, which is NN-dimethyltryptamine, which is a hallucinogenic indole molecule, is more basic. We have the option of this nitrogen of the indole ring, as well as this nitrogen that is an alkylamine. The lone pair on the nitrogen of this indole ring is required to complete the aromaticity of the indole ring, and therefore is typically not available to do reactions with acids or electrophiles. So this nitrogen is generally not considered a basic amine. The nitrogen here on this side group, however, is free to react with acids and electrophiles. So this is going to be the most basic nitrogen in this molecule. Let's do a quick recap of some of the things that we discussed in this chapter. Amines are derivatives of ammonia. The basicity of arylamines is lower than that of alkylamines. The nitrogen lone pair electrons in arylamines is delocalized by interaction with the aromatic pi system, and therefore aromatic or arylamines are less basic than alkylamines. Compounds that contain one or more nitrogens that are shared in a ring are referred to as heterocyclic amines. Alkylamines are prepared by SN2 reactions of ammonia or an amine with an alkyl halide, or by the Gabriel-amine synthesis. In reductive amination, a ketone or an aldehyde is treated with an amine in the presence of a reducing agent such as sodium borohydride. Amines can be synthesized through the Hofmann and Curtius rearrangements of a carboxylic acid derivative. In the Hofmann elimination, typically amines will undergo an E2 reaction, giving you the less substituted alkene or the Hofmann product. And the Sandmeyer reaction is a reaction that allows us to convert arylamines into several different substituted aromatic compounds by the attack of a nucleophile with a diazonium salt intermediate. Let's go over a few examples of the reactions we covered in this chapter to review these reactions. We'll start off with a reaction involving a nitrile and reacting it with lithium aluminum hydride. In the second reaction, an aldehyde is also reacted with lithium aluminum hydride. In the third reaction, we're going to reduce a nitro group in this substituted aromatic compound with hydrogen gas, palladium on carbon, or tin chloride and an acid. In the fourth reaction, an alkyl azide will react with lithium aluminum hydride. In the last reaction on this slide, we're going to take a ketone, add a primary amine, and sodium cyanoborohydride at a pH of 3 to 4. The first reaction on this slide, we're taking a nitrile and we add in lithium aluminum hydride, which of course is a hydride reagent that will attack the carbon of the nitrile. It'll occur twice, and then the two negative charges on the nitrogen will react with the protons on this acid to overall convert the nitrile into a primary amine. The combination of a hydride and an acid essentially is equivalent to adding H2 gas in a hydrogenation reaction. In the next reaction, we're going to take an amide, and unlike most acid derivatives which react with lithium aluminum hydride, instead of getting a primary alcohol, with amides, we generally get an amine. The reason is the carbonyl is a better leaving group than the nitrogen. So after the addition of one equivalent of the hydride to this carbonyl, the OH that results will be eliminated by the lone pair on this nitrogen, and the imine intermediate will be eventually reduced into this amine. The first two reactions were reactions that we previously discussed in other chapters. We also discussed the reduction of a nitro group into amine. That can be done under hydrogenation or metal reduction. Anytime we add a metal in an acid, it's again equivalent to adding H2 gas. And that will be another method to reduce a functional group such as a nitro group. Azides can be reduced with lithium aluminum hydride and acid into a primary amine plus N2 gas. The last reaction here is an example of a reductive amination where we take a ketone or an aldehyde. In this case, it's going to be a ketone. We're going to add an amine. We're going to be using a primary amine in this example. That primary amine will add to the carbonyl carbon, initially form an imine intermediate, which would then be reduced by the hydride reagent into an amine. In this reaction, we're going to take an amide. We're going to add Br2. We're going to add Br2 and base. In the next reaction, we're going to use a different acid derivative, which is an azoacide. We're going to heat it and then add water. Next, we're going to add base to the phthalimide, followed by an alkyl halide, a primary alkyl halide, and then finally hydrolysis conditions, which is base and water. In the next reaction, we're going to add an excess of methyl iodide, followed by silver oxide, water, and heat. And then lastly, we're going to add nitrous acid, sulfuric acid, followed by copper chloride. The first reaction on this slide is an example of the Hofmann rearrangement, which starts off with an amide. We're going to add Br2 to activate the 1,2 alkyl shift, which will eventually lead to the elimination of the carbonyl and combination of this alkyl group on the left of the carbonyl with the nitrogen and the methyl group attached to it. So as a result, we get an amine plus carbon dioxide as a byproduct. The next reaction is a Curtius rearrangement, which involves an azoazide, which when we heat will be rearranged into an isocyanate. Water will react with it to form a carbamic acid, and eventually it will decompose to form an amine plus CO2, which is not shown here. Notice in this reaction, similar to the Hofmann rearrangement, the carbonyl will be eliminated as CO2, and the alkyl group on the left of this carbonyl would join with the first nitrogen of the azide to form this amine. We're going to lose the second and third nitrogen from the azide as a nitrogen gas molecule. In the next example, we're doing a gabrioamine synthesis where base removes this hydrogen. That will make the nitrogen more nucleophilic. It will attack the carbon with the leaving group. We'll add a propyl group to this nitrogen, and then base and water will lead to hydrolysis of both of these amides, releasing the internal nitrogen plus the propyl group that was attached to it. And then we'll also have the rest of the molecule be eliminated as a dicarboxylic acid. So this carbonyl and this carbonyl will become carboxylic acids. The next reaction is an example of the Hofmann elimination, where excess methyl iodide will alkylate the nitrogen to the maximum extent. In this case, we're gonna add 2 more methyl groups. Then silver oxide and water will produce hydroxide ion, which will lead to an elimination reaction. The base will remove the least hinder hydrogen on the carbon that is adjacent to the carbon containing the nitrogen. There are 2 possibilities. We can remove this hydrogen on this side, or the first one that I drew up here. This is less hindered, so we're going to remove that one. That's typical of the Hofmann elimination. And we're going to get the anti-Sysef or the Hofmann alkene. Last reaction is an example of the Sand-Meyer reaction, where nitrous acid and sulfuric acid will turn the amino group into a diazonium salt, which is a great leaving group. And then that will react with copper chloride in a radical mechanism to add a chlorine. On this slide, there are 3 different examples of the Sand-Meyer reaction. They all start with an aniline, and we're going to add nitrous acid and sulfuric acid. In the first reaction, the diazonium salt will react with copper cyanide. In the second reaction, it will react with hypophosphorus acid. And in the third reaction, the diazonium salt will react either with acid and heat or a copper catalyzed reaction with copper nitrate and cuprous oxide plus water. In the first reaction, the diazonium salt that is formed as the key intermediate in the Sand-Meyer reaction will react with copper cyanide. That will replace the diazonium salt with a cyanyl group. Hypophosphorus acid will reduce the diazonium salt and put a hydrogen in its place. So this is a good way to remove an amino group. And in the last reaction, we're going to use either acid and heat or a copper catalyzed reaction with water to convert the diazonium salt into a hydroxyl group. In this synthesis problem, we're going to convert nitrobenzene into a meta-substituted dihalide benzene compound shown here. In this synthesis problem, we need to convert nitrobenzene into a meta-substituted dihalide benzene compound. This presents a challenge, at least initially, based on the reactions we previously learned, because normally the halogens are ortho-para-directing, so it would be very difficult to use bromine, for example, to add a meta chlorine. However, based on the Sandmeyer reaction we learned in this chapter, we can use an amino group to essentially add other substituents, and the precursor to the amino group, which is the nitro group, as we know, is a meta director. So using that information, we can put the synthesis together. The nitro group we can use to direct the chlorine to the meta position through a chlorination reaction, which we previously learned. So adding Cl2 and iron trichloride will lead to adding this chlorine at the meta position compared to the nitro group. Reducing the nitro group now into an aniline by either hydrogen and palladium or a metal and an acid reduction, we can now get this amino group, which is the precursor to the Sandmeyer reaction. This is one of the reasons why the Sandmeyer reaction is so versatile. We can convert this amino group into a bromide by adding nitrous acid and sulfuric acid followed by copper bromide. Note that we could change the order of some of these steps. For example, we could add a bromine here through Br2 and iron tribromide. And then when we get to this step, if we add copper chloride, we could add the chlorine and get the same product.